Hello everyone. Today we're going to discuss about LLVM and its applications in GPU computing. LLVM stands for Low Level Virtual Machine. Myself Milap Pandey and I have my team members.
Myself, Gayatri Joshi.
And myself, Chetna Shrestha.
Thank you so much guys. So today we're going to start with an overview. LLVM, originating in 2000 at the University of Illinois, is a modular, extensible, open source compiler infrastructure. Its design allows independent development of front-end languages, optimization, and code generators, ensuring adaptability to evolving requirements. With efficient optimization, passes, and code generation techniques, LLVM produces high-quality machine code for diverse platforms. Widely used in compiler construction, optimization, and analysis, LLVM drives innovation in software development.
Okay, so now let's talk about LLVM and its history. So, LLVM is a compiler infrastructure project that originated at the University of Illinois. Initially developed by Chris Lattner as a research project in 2000, LLVM aimed to provide a modern, flexible compiler framework. LLVM started as a research project focused on compiler technology, code generation, and optimization. The project gained momentum with contributions from various individuals and organizations, leading to its evolution into a full-fledged compiler infrastructure. LLVM's journey from a research project to a leading compiler infrastructure reflects its importance and impact on modern software development. As LLVM continues to evolve, it remains at the forefront of innovation in compiler technology, enabling efficient, scalable, and performant software solutions.
So now we'll get into the workflow of LLVM. It mainly contains three things: front-end, optimizer, and back-end. Front-end is the stage where the source code is converted into an intermediate representation called LLVM IR. Optimizer. LLVM IR generated by the front-end stage is then passed through the series of optimization passes. These optimization passes analyze IR and perform various transformations such as elimination, reduction computations, rearranging instructions, etc. to make code more efficient. Backend. In backend stage, the optimized IR is then converted into machine code that can be executed by specific computer architecture. This stage involves tasks like instruction selection, register allocation, and code emission.
Yeah. So now we're going to talk about applications of LLVM. LLVM has a very diverse range of capabilities in terms of integration. So LLVM can be integrated in different fields of the computation fields, such as scientific simulations, image processing, deep learning, performance enhancement, and portability and scalability. We have seen how LLVM can be used to optimize the working of all these things. LLVMs is continuously optimizing the work of AI, ML, IoT, and different fields in computer science and scientific fields.
Okay, so now we will focus on one particular application of LLVM. So leveraging LLVM for GPU. So graphics processing unit programming harnesses the parallel processing capabilities of GPUs for computationally intensive tasks. They excel in tasks requiring massive parallelism, such as graphics rendering, scientific simulations, and machine learning. LLVM enables code portability across different GPU architectures, reducing development overhead and improving platform capability. LLVM's optimization capabilities optimize GPU accelerated code for improved runtime performance and efficiency. Integration with LLVM based languages and frameworks enables seamless interoperability between GPU accelerated and CPU based code.
Now we'll understand about CUDA LLVM compiler. The CUDA LLVM compiler allows developer to write code that can take advantage of massive parallelism and computational power of NVIDIA GPU, while still benefiting from the optimization and advanced features of LLVM compiler infrastructure. We'll move forward. There are mainly six stages of LLVM compiling: uh, front end, LLVM IR generation, CUDA specific optimization, back end, GPU code generation, and linking and execution. Starting from the front end, CUDA LLVM compiler has frontend that can parse CUDA C++ code, which is an extension of standard C++ with additional keywords and functions for programming GPU. LLVM IR generation, the CUDA C code is converted into LLVM IR, just as in simple LLVM workflow. CUDA specific optimization does the CUDA LLVM IR goes through series of optimization passes, including some optimization specific to CUDA and GPU programming. The backend of CUDA optimizes the CUDA CUDA LLVM backend, which generates machine code that can run in NVIDIA GPUs. GPU code generation, the CUDA LLVM compiler generates two types of codes: device code and host code. The device code is the code for GPU, and the host code is the code for CPU. Device code runs on GPU, while the host code is responsible for setting up GPU execution, transferring data between CPU and GPU, and managing overall execution flow. Lastly comes linking and execution. Finally, the generated GPU and CPU codes are linked together into single executable that can run on a system with an NVIDIA GPU.
So now let's talk about NVIDIA Compiler SDK. So what is a software development kit? It is a set of software tools and programs provided by hardware and software vendors that developers can use to build applications for specific platforms. SDKs help developers easily integrate their apps with the vendor's service. So the NVIDIA Compiler SDK also provides developers with documentation, examples, and tested binaries to kickstart GPU-accelerated compiler projects. The components include an optimizing compiler library that is a live NVVM, common math function library that is a live device, and sample code illustrating compiler SDK usage. Now, I will talk about the CUDA software developer environment. The CUDA software development environment provides all the tools, examples, and documentations necessary to develop applications that take advantage of the CUDA architecture. The advanced libraries include BLAS, FFT, and other functions optimized for the CUDA architecture. The C runtime for CUDA provides support for executing standard C functions on the GPU and allows native bindings for the other high-level languages such as Fortran, Java, and Python. There are various tools like NVIDIA C compiler, CUDA debugger, CUDA visual profiler. The documentation includes the CUDA programming guide, API specification, and other helpful documentations, the SDK code sample, and documentation that demonstrates best practices for a wide variety of GPU computing algorithms and applications.
Let's study more about the CUDA architecture. The main components of CUDA architecture are streaming multiprocessors. Each SM contains multiple CUDA cores, which are the computational units that execute the instructions of the program. When you run a CUDA program, the CPU sets up the execution environment on the CPU and launches the program code, called the kernel, on the GPU. The kernel is divided into many threads, and these threads are organized into thread blocks. These thread blocks are then distributed across the available SMs on GPUs. These SMs have access to various types of memory, such as the registers, shared memory, global memory, and constant memory. Overall, NVIDIA CUDA architecture enables GPUs to perform highly parallel computation efficiency by leveraging the massive number of CUDA cores and various types of memory units available on GPU.
NVIDIA's CUDA compiler utilizes LLVM compiler infrastructure to optimize code for NVIDIA GPUs, applying techniques like loop and memory optimizations. NVCC enhances CUDA code execution. NVIDIA collaborates with the LLVM to ensure full GPU support, accelerating parallel computing for various applications from scientific simulations to graphics rendering.
Okay, so now let's talk about maximizing GPU performance with LLVM. So LLVM offers a versatile framework for optimizing and accelerating GPU code across diverse application domains. Integrating LLVM with GPU programming overcomes challenges and leads to significant performance gains and enhanced portability. The future of high-performance computing increasingly relies on the synergy between LLVM and GPU programming for advanced applications.
So, in conclusion, LLVM is pivotal in facilitating efficient code generation, optimization, and portability across diverse computing architectures. From its inception as a research product to its widespread adoption, LLVM has revolutionized compiler technology and software development, whether accelerating GPU computing, enabling just-in-time compilation, or optimizing code for embedded systems. LLVM continuously pushes software development boundaries. As LLVM evolves, its impact on computer science and software engineering remains profound, driving innovations and scalability. Embrace LLVM to unlock faster, more efficient, and portable software solutions, maximizing project potential in dynamic computing landscape. This is all for the low-level virtual machine. Thank you so much for watching this presentation, guys.